Hi again, everyone. It's Dan Sannick with ICLR. Thanks for joining us. There's still people in, but we're about 1 minute after 1 p.m. Eastern time, so we'll get started. We got a pretty good crowd here today. So thanks again for joining us. I know we'll have a great presentation by Professor Bitsuamlak from Western University. Before we get started, we just wanted to remind everyone of the question and answer approach that we use here. So if you could ask questions anytime throughout the webinar using the Q&A function that you'll find on the bottom of the webinar platform window. Just click the Q&A function, enter your questions, and we'll save all of the questions to the end of the presentation, and we'll have some time for facilitated discussion with Professor Girma Bitsuamlak. But please do post your questions throughout the webinar if you have any. And also, before we get started, I just wanted to note that we haven't yet released our schedule for next year's Friday Forums, but that should be coming out soon. So watch your inbox for notices from Tracy Waddington, because we've got a good schedule lined up. We just haven't quite released it yet. So with no further ado, we're very happy to have Professor Girma Bitsuamlak from Western University. Professor Bitsuamlak is certainly one of the top researchers in wind engineering in Canada, and it'll be great to hear from him today. Professor Bitsuamlak is a Canada Research Chair in Wind Engineering, and also Director of the Boundary Layer Wind Tunnel and Windy Research Institute at Western University. So we're very, very happy to have Professor Bitsuamlak, and with that, I'll pass it over to Dr. Girma.
Thank you very much, Dan, for a great introduction. Good afternoon, everyone. Today we'll be talking about tall mass timber buildings. More specifically, we'll discuss about their safety and some serviceability issues associated with tall mass timber buildings. Before I forget, I would like to acknowledge this is an outcome of a research collaboration between University of Western Ontario, University of British Columbia, and FP Innovations. And majority of the work is the outcome of the PhD work from Dr. Matthias, who was our former PhD student, now works with WDI, and another scientist from FP Innovation, Samuel, continued his work, and I want to acknowledge their contribution. Okay, the agenda includes, I'll introduce wind engineering. There is always a slide in my talk, what I usually call wind engineering 101. Then we'll discuss about the specific challenge as it relates to mass timber building. You know, designing tall buildings for wind is not something new. Since early 1950s, 60s, since we started using wind tunnel, things have become more streamlined, you know, skyscrapers made of concrete, steel, other composite materials, and timber is joining this club, you know, and that's what makes it new. And we'll focus on the specificity of mass tall timber building, and we'll see what are the challenges. We'll focus on the dynamic response. I will also introduce the performance-based wind engineering design, performance-based wind design approach, and a majority of the houses in North America, they are made of timber. You know, not necessarily the tall buildings, even the mid-rise, low-rise buildings, and there's a chance that they could be exposed to tornado, and we have been working also in that type of research. I will introduce some of the outcome of those type of research. Okay, why do we need wind studies? It's because majority of our construction is in the coastal lines and it's exposed to hurricanes, even in the middle of the continent, for example, is exposed to dense synoptic winds like tornado, downburst, and other strong synoptic winds. and we need to design them, otherwise the picture that you see on the slide will happen. And from tall building perspective, majority of the tall buildings are well engineered. Then you may not see as significant damage as the less engineered low-rise counterparts, but there is another motivation, the economy. You know? When you try to design buildings with a blanket approach using building codes and standards, that may or may not represent accurately what you are designing. Chances are you could err towards conservatism. It's not always the case. Sometimes you may not be even conservative, but majority of the time, because we use an envelope approach, we tend to be conservative. And for example, on such mid-rise tall building, there was a study done by RWDI. If you design using code and wind tunnel based, you'll see the saving in the cost on this mid-rise type of building, you know, 2.4 million versus 1.7 million, you know. So you'll save significant if you 27% of the cost. So there is an economic incentive as well. Western has a good tradition in wind research. Sorry, I was closing the door. Thanks to our former members, you know, like Professor Davenport, who is considered as a father of wind engineering, since he established the bound layer wind tunnel in early 1960s. Since then, Western has been a place to do wind research, and primarily because we have a critical mass of highly experienced wind engineers, professors, research engineers, and more than 60 graduate students, most of them PhD students working on wind-related topic. And we are also blessed with state-of-the-art experimental facilities to bound layer wind tunnels, large-scale failure study lab, the Insurance Research Lab for Better Homes. And there is also another lab for avian research, you know, bird aerodynamics and biological aerodynamics. And more recently, during the last decade, we added also state-of-the-art facility, windy dome, that's capable of generating tornadic and synoptic wind. In addition to this, we also augment the experimental research heavily with computational research, you know, using the facilities at the SharkNet supercomputing facility and the computational resource available in the South Ontario Scientific Innovation Platform and the cluster we have at WinE as well. One of the genius of Alan Davenport is his ability to convey very complex problems in very easy to understand manner. You know, one such contribution is Alan Davenport wind loading chain. You know, when one wants to design a structure for wind, we have to accurately model, you know, each of the elements that forms the chain. You know, it starts with from the wind climate. The wind climate, the first in the chain, primarily deals with quantifying what is the design wind speed, what type of wind is happening in the particular place where we wanted to design the structure. Is it hurricane? Is it tornado? Is it downburst? What's the frequency? Then this kind of information can be obtained, particularly for straight wind from airports. You know, we analyze the airport data. If the place is remote and there is no airport or measurement data, we rely on climate models. And majority of the time we target the design wind speed based on what the code says. But if there is no local code or if the code is too old, you know, then we rely on this kind of airport data. Of course, in any system design, the outcome of that system or the response of the system is dependent on the input you provide. If the input is not correct, there is no way the output will be correct. So this is the most important step in the wind load chain. Then once we know for what intensity of wind, what type of wind we are designing, then we look into other parameters that affect the wind response. Wind is affected by whatever it sees. For example, the terrain, the surrounding building. I hope you will see my mouse moving around. If, for example, you have a tall building in the middle of the suburban compared to in the middle of the downtown core, the two locations will produce different kind of wind. In fact, if you look into the blue CFD animation, if you look at this building, if you are studying this building sees a wind that's affected by the upstream buildings. Mind you, this continues up to 5-10 kilometers. Anything that you see up to 5-10 kilometers may impact your building. The one upstream will see a different type of wind compared to the one behind it and the one after it. So we have to assess the impact of surrounding buildings, the impact of upwind exposures. That's why we usually categorize exposures in suburban, urban, open suburban, or any combination of this. In wind tunnel, we model it through this kind of roughness. What is within a couple of blocks, we reproduce it accurately, but beyond a couple of blocks, we represent it in terms of roughness. Whether you do this, whether you decide to conduct a preliminary computational wind load analysis or accurate wind tunnel analysis, you need the consideration of the upwind terrain. Mind you, this gets complicated even when the building is located in orographic regions where there are mountains and valleys. The impact of those geographic features or topographic features has to be assessed as well. Then once you characterize the wind closer to the study building by considering the exposure conditions, then the next step is to look into the specific building shape. Aerodynamics in layman's term mean shape effect. My favorite example is airplanes, they fly because they have a certain shape. For example, on the wing, on a strong winter, if there are icing forming on the wing, and some irregularities on the shape, even it could cause issues, So aerodynamics is really closely tied with shape, Then the study shape, the shape of the study building has to be accurately modeled, Rectangular buildings produce different type of forces compared to even a square building. Square building different from circular, elliptical. If you have balconies or corner details, it produces different type of load compared to tapered one or twisted one. So all those geometric alterations lead into a different kind of load, and we have to accurately model it. For tall buildings, we are primarily concerned about lateral load. Of course, we have to design the cladding, the roof properly. But for low-rise building, primarily we are concerned on the roof. But we have to also worry about the windows, doors, and things like that. And the third parameter is the dynamic effect or the mechanical effect. What that represents is when you have flexible structures, mind you, the flexibility, wind is not like a smooth load. As you can see from the CFD animations, you have a turbulent wind flow coming and hitting your structure. Usually the frequency content of that turbulent flow is less than 1 hertz content. Then what the implication of this is, if you have a structure whose natural frequency is less than 1 hertz, most likely it could be excited, by the turbulence in wind. But majority of the short buildings, like 10-story and lower, they don't get excited by wind unless you have long span roof or some flexible members on the structure, So that is important. When you have flexible structure, as the structure flexes and sways under the action of the wind, it also alters the load. There is what you call aeroelastic feedback, Then we have to capture that. I have an example here. A tall building swaying by the action of the wind, Basically, wind is hitting it on the wider side, but the building buffets or vibrates in the direction of the wind and in opposite direction to the wind, which we call across wind effect, which I will explain later using one video. If you have antennas, for example, this antenna is an antenna on the top of the 350-meter tower building. When you have flexible antennas like that, this has almost a 30-meter range. You have to study it separately because it's so flexible. You see the dynamic model in the wind tunnel behaves like this. You have buffeting movement, you have across wind movement and things like that. So this load would be different from the same type of structure if it was rigid. That is what the dynamic effect emphasizes. Then if you consider all these parameters, most likely your wind load will be accurate. The deflection you calculate will be accurate. The acceleration that you calculate from your model will be accurate. Majority of the discussion so far was based on straight wind, but as you all know, even in South Ontario, there is a Northern Tornado Project that is led by Professor Greg Kopp at Western, and they run after and chase tornadoes, and they counted more than, if I remember correctly, 29 tornadoes in South Ontario this year alone, and in Midwest in the United States, or in the continent of North America, more than 1,700 tornado landfall. So we have to design at least the essential facilities for tornado, like our hospitals, police stations, fire stations, and things like that. And at least we should have safe rooms for residentials. In order to do those kind of designs, we have to determine the tornado load accurately. Luckily, at Western, we have the windy EDO, and it can produce tornadic flow like this. Or downburst flow, like a jet is coming from this, and you will see creating this kind of vortex, and it's hitting a 5-span full aeroelastic transmission line test object here. We are also advanced in modeling tornado computationally thanks to SharkNet and their amazing technical support. You can do also computationally. Actually, when it comes to this kind of complex flow, the computational model is almost as useful as the experimental facility as well. Okay, shifting to today's main topic, why tall mass timber? If you see, more than 39% of the greenhouse emission is due to buildings. Then, if you start building with sustainable material like timber, you can knock off that contribution from building. Canada, we make up 9% of the world's total forest area, and it is the third most forested country in the world. And if you use timber structure, the embedded energy for timber is 5 times less than concrete. So these are some of the incentives why we could use. With the proper forest management, actually, without affecting the forest. The forest needs to shade also some of the old trees. Just by utilizing those kind of trees, we could build many houses, out of timber. And since the CLT was invented, even the construction of timber is becoming taller and taller thanks to this kind of cross-laminated timber products and glulam columns. This could be structural members. And with encapsulation, I'm not a fire expert, but my colleagues, they tell me the fire performance of CLT is far more than the 2-hour rating that the building codes require. Inspired by this, there is mushrooms of tall building throughout the world. Some of the examples are the 9-story building in London, the Forte 10-story building in Melbourne, and the Life Cycle Tower 1 in Austria, and there is one building in Minneapolis, and Oregon in Quebec City. Actually, one of my PhD students, Samuel, is monitoring this building. I'll be talking about it. And the UBC Brooks Common student dormitory building, 18-story building, except the concrete core and the first floor, everything is timber. Actually, we'll be talking about this building as well. And the tallest is the 18-story building in Norway. It is 85 meters tall, and there are many in the making, in the news, Yes, there are some challenges when you build tall mass timber buildings. I must say, most of Canada, like I know British Columbia, Ontario, Quebec, they have approved up to 12-story buildings. I'm sure with engineering design, more taller buildings can be also approved, like we were working with Sidewalks Lab in Toronto and on 35-story tall mass building, just before the cancellation of the program. So the sky is the limit, but we have to acknowledge some of the limitations and address them accordingly. What are these limitations? Timber has low lateral stiffness, and it is lightweight in nature, and we need some mass, to kill the vibration at the top occupied floors. And there is also higher mode effects that may contribute to the load. Drift under service level wind load is higher. Habitability risk due to along and across wind acceleration. The vibration issue has to be looked into. And like any other building, the localized fatigue issues on connections, cladding connections, and things like that has to be looked. When you design tall mass timber for timber, like the global forces in addition to local forces has to be looked because of the lightweight of the building, Then looking at these issues, we started asking some fundamental research questions. For example, how tall can a mass timber building go without wind-induced vibration issues? And what is the best strategy to assess serviceability and things like that, Okay. When we started working on timber building with my collaborators, researcher at UBC and FP Innovations, we wanted to know how tall can we build, without having significant wind-induced vibration issues on the top floors, To nail that, we adapted the form that SOM put forward at that time, the one you see on the left. We were inspired by this design, and we adapted that form, and we completed the design, and we detailed it for 5 different height tall mass timbers, as you can see in the figure, for 10-story, 15-story, 20-story, 30-story, and 40-story building. So I will be talking about the performance of this and which height, beyond which height we will start noticing the acceleration issue and things like that. And the second one is the UBC Brooks Common building. Out of abundant caution, the structural engineers put a concrete core, but as a researcher, we said, okay, what will happen if we knock out the concrete and make it fully with CLT, cross-laminated timber. And you will see the result of that research, one with reinforced concrete as it is designed and built in UBC, and the other is theoretical model where we knock out the concrete core and replace it with CLT. And the third example is the shorter building. We did a detailed tornadic investigation as well. Okay, coming back to the first project, as I mentioned earlier, this design was inspired by the preliminary design structural form that was put forward by SOM in the public domain. We took that and we completed the design. Basically, it has perimeter concrete beams and link beams that connects the core and the shear wall. Otherwise, all the columns, the floor, the shear walls are CLT. More than 90% of the structural system is CLT. Then one thing we used was the HSK connection. In fact, that detailing is what makes it different from what was proposed by SOM. Then once we completed the design, following this design process, I will provide the reference for detailed design guideline. There are a couple of papers that came out of this work. Any interested person can look into those papers. Then if we zoom into the structural property or the dynamic property of the building, I just pulled two properties, one for the 40-story and the other for the 10-story. As you can see, the 40-story building, although it is only 40-story high, all the first 5 modes have frequency less than 1 Hertz. So typically, majority of the tall building, it is only the first 3 frequencies that will become less than 1 Hertz, unless it is really unique super tall building like the Chicago Spire or Burj Khalifa or some of this tallest building, But majority of the tall buildings that we see in Toronto, for example, they're only the first 3 modes typically is excited by wind. But a 40-story timber building could have a natural frequency up to the 5th mode with a magnitude less than 1 Hertz. That means the 4th mode, the 5th mode could be excited by wind. Even the 10-story building, the first few modes are less than 1 Hertz, So there is a chance that it could be excited by wind as well. So that's what makes them special. They are flexible, hence we have to deal that during the design process or the mitigation process. Okay. These are some of the definitions. Wind, usually straight wind, has this kind of boundary layer. The blue shows the mean profile and the green profile is instantaneous. Usually if you take one snap of profile, you get the green. But if you take multiple of them and average, you get the blue profile. And it is this type of wind that excites our building. And whenever I use axis Z, it is vertical, Y is in the direction of the wind, X is in the across wind direction. And you have moment in X direction, moment in Y, and torsion loads, And the angle of attack, the wind can hit the building in different angle of attack direction. Usually in wind tunnel, we study 36 different wind direction and we design for the worst of those. Okay. And it is important also in the design of wind, one has to produce the mean velocity profiles shown by the dark color and the turbulence intensity shown by the red color. In this study, we looked into different kind of exposure, open country, suburban, urban. For example, if you compare open and suburban, open has more flat, big velocity close to the ground. Suburban has less velocity close to the ground, but more fluctuating velocity or turbulence close to the ground. So that's the signature of open and suburban. I'm intentionally explaining this because you'll see the impact on tall mass timber response, and we need also to characterize, whatever we do, the wind simulation in the tunnel, it should have similar frequency content with the real wind, because that frequency content, if you are off, you may or may not excite a tall building. So you need to match that as well. Okay, then after matching those, we conducted 5 different tests. Yes, there could be an approximate way to get from one of the building the other nodes, but we didn't want to introduce any approximations, the ground effect and everything. We wanted to be estimated accurately, and we conducted a pressure test for 5 of them. And pressure test basically looks like the one you see on the bottom right. You have openings, holes, small holes with a diameter of maybe little less than 2 millimeters. Then at the back you attach it. If you open the model, it looks like this. You attach a tube with a tube, and at the end of the tube, one end is the hole on the building, the other end is attached with pressure transducer. Basically, it measures the voltage. Then as the wind puffs inside the wind tunnel, then the voltage changes, and we measure those, and we have calibrated what kind of voltage change correspond to what type of pressure, and through that, basically at all these dot points, we measured the pressure. Once you have the pressure on those points, you multiply it by tributary area, and you can calculate all kind of force that you need, the shear force, the base, and floor by floor load, whatever you want, for your design. Okay, I want to draw your attention to this video. Usually this is what happens, like when we put a smoke in the wind tunnel, this is what you visualize, and as you can see, there is oncoming turbulence. It is not smooth. It is, you see the change in streamline and the fluctuation and things like that. And as it hits the first leading edge, both on the left and the right, or as you see it in your image, bottom and top, you have a flow separation, and you have shear layer turbulence added, Then you have a wake turbulence as well, One thing interesting is if the wind is coming from left to right, yes, there will be along wind forces, along wind vibration and things like that. But what is unique in wind engineering is while the wind is coming from left to right, this vortex sheds at different time from the bottom. This alternate vortex shedding produces a force in the across wind direction and shakes the building in perpendicular direction. Actually, this produces majority of the time significant vibration or acceleration, and that's what we should pay we have to pay attention to that, in addition to the along wind responses. In fact, if you look at this, it will show what I was saying clearly. These are spectra of the forces measured at the base, and the first 3 spectra are for 40-story building using open country exposure, imagining like your tall building is like in the outskirts of Toronto, for example, or suburban, like in the suburban part of Toronto, and urban if it is in downtown Toronto, Then when you have those kind of locations, the response are different, especially the one like the 3 colors. Where did I define them? Okay. Usually they are the torsional and the sway responses, And if you see this, you have for the 40-story building at reduced frequency, natural frequency of the building divided by the velocity at the height of the building times some front dimension. At reduced frequency of 10 to the power of -1, around 0.1, you have significant response, that is primarily due to the vortex shedding that I was trying to describe, Then if your natural frequency of the building corresponds to the one that produces a reduced frequency of 0.1, then you have a resonance. The building sways like significantly, producing big accelerations, So, but this kind of reduces as you, at the height reduce, the peak here for 30-story building, for example, here is slightly less than the 40-story. The 20-story building is significantly less than the 40-story. And at 10-story, you don't see even that peak. The ground effect and everything dominates, and you don't see that. And the other thing, as I said earlier, urban areas, the velocity is low at the building level compared to open areas. So what it does is it shifts this reduced frequency to the left, bringing majority of the reduced force just to coincide with the peak response that we see in the spectra, and that could produce issues, So we saw the impact of turbulence, we saw the impact of height, We have to consider all this when we decide to place tall mass building, whether it is in open or suburban or urban areas, When you look at explicitly the top floor acceleration, I'll try to walk you through this heavy slide. The first column are responses for a 10-story building, the second for 15, and it goes on, and the last one is for 40. And you see for each of the building, you have 3 plots. One is if the building is located in open country, the other is in suburban, and the third row at the bottom is urban. Now, and there are also 2 red lines, These are the serviceability limit states, Like if you have office building, for example, the NEBCC stipulate that the acceleration that the building produces on the top occupied floor should not exceed 25 milli-G, milli being 10 to the power of -3, G being gravitational acceleration, which is 10 meter per second square. Then if something is greater than 25 for an office building, then it's not acceptable. If something is more than 50 milli-G for residential building, residential is occupied majority of the time, so the NEBCC has stricter regulation of 15 milli-G. Then if you have a 10-story in open country or suburban country or urban exposure, you don't have any issue. Also, for each of the graph, there are multiple plots, Each of them, they correspond to different level of damping. The definitions are given on the lower slide. The dark uses 1% damping. The second uses 2% inherent damping. If you add additional external dampers, you could have 3%, 4%. And if there are such damping, we just did the analysis. But the inherent structural damping, I don't think it will exceed more than 3%. Actually, I will show you some monitoring we did. We are getting in the range of 2 to 2.5, So it's fair to assume, timber building has 2% inherent damping, and we pay attention to that 2%, the one with gray color, Of course, one of the most uncertain parameter is the damping ratio. It depends on the connection, the structural material, the participation of non-structural members, the soil foundation interaction. Since it is such a complex parameter to determine, there is a lot of uncertainty. That's why there are a lot of effort out there to monitor full tall buildings and estimate the inherent damping ratios, But for our case, we'll focus primarily with the gray line, Then when you come to 15-story, if that 15-story is located in suburban area, you have no issue of acceleration, at least if the structure resembles to whatever we designed for, Of course, every structure is different, It is on the context, under the context of the building that we design. It's a typical tall mass building, tall mass timber building. Then, but if you see for certain wind direction, when a wind is hitting the building in a perpendicular direction, that's where majority of the vortex shedding happens. You are violating, for example, the residential building. So if you are building a 15-story in open terrain country, you may encounter some acceleration issues, If it is office building, it's okay. Then the 20-story, it will have issues definitely for residential, for residential building, but for office building, it is okay. So technically, without any issue, you can go up to 20-story. But for 30-story and 40-story, you can see a big chunk of it, is beyond the criteria of the residential building. Even for 40-story building, if you see the gray, it is above even the office criteria. The 30-story, it is barely satisfying the residential criteria in suburban. But if you have 30-story in open exposure, you cannot satisfy the residential, So basically this gives you, so 30 seems the critical height, up to 20-story, you are okay. When you have a 30-story or 40-story, you may violate the residential. Then, of course, it's not the end of the world. What this means is you have to bring other solutions by way of aerodynamic mitigation, by way of using external dampers or structural fine-tuning that I will show in the next slide. For example, if it was a a timber core, you replace it with steel, the issue, with concrete or steel, the issue will disappear. I'll show you some result on that. I think I will pass this one. This is just more accurate aeroelastic model to validate the pressure model. And there was a good agreement, the error of difference is exactly, majority of the time it is 5%, but it did not exceed 10%. That's the typical difference between aeroelastic and aerodynamic tests. So that's what we wanted to confirm, and we confirmed it. As I mentioned earlier, the response is dependent, especially the acceleration is dependent on the stiffness, the mass, and the damping. There's big uncertainty in the damping, and one of my PhD students, who happens also to be FP innovation scientist, is a part-time PhD student. He's from Quebec office in FP innovation, and he monitors this Oregon build. The first, when it was built, it was the tallest all-wood building. Now, of course, the Brook Commons came, the Norwegian building came taller than this, but it was one of the first all-wood building during its construction. Then they have accelerometer top floor, and they were monitoring it, and this is installed underneath the top floor, and this is the preliminary outcome he just provided to me yesterday. These are the distribution of the damping ratio. If you fit log normal, it looks like the best fit. And with log normal fit, you are getting 2.5% of inherent damping, This kind of experiments are very useful, because this is the most uncertain parameter. We don't know much about it, Okay, if you want to know the details about the design in the tall building and the dynamic analysis, please refer to these papers. Okay. Now getting towards the performance-based design. Before I explain the performance-based wind design, I would like to draw your attention to design of tall building as it is done now. Currently, tall buildings are being designed to meet acceptable level of public safety through some limit state and serviceability, like primarily controlling the top floor acceleration and the top deflection and things like that. And in this type of design, the first significant tilting point is considered an ultimate limit state. So all this elaborate, complex, tall buildings subjected to very dynamic load, at the end of the day, they are designed as linear and elastic design, period. We never design, at least as far as I know, as non-linear design, so non-elastic. We never cross the first yield point, And also the uncertainties that are inherent in the damping ratio, in the wind. Actually, the most significant uncertainty comes in quantifying the wind itself, the design wind speed, the inherent there. And there are all parameters in the structural property. For example, when you start using new construction materials like timber, very complex material, then there are uncertainties, and majority of them are, the uncertainty in the traditional design process is through safety coefficient, and it doesn't lend itself to be modified or followed when you have new construction material or new design method, then there should be a better way of uncertainty propagation. This too, the desire to utilize the nonlinear capacity of the material strengths and the desire to be using new construction material is pushing us towards performance-based design, By the way, the reason why we don't go beyond the yield point in wind engineering, you have significant mean component in addition to the fluctuation. For example, earthquake-like loads are primarily dynamic. The mean is towards zero. But in wind, you are pushing the building, and in that new deformed position, you are vibrating it. Then if you pass the first yield point, then there is a permanent drift. Then there is what you call damage accumulation. That's the reason why we limit ourselves in the linear elastic range. But there are now new technologies, new ways to counter this type of effects, and hence we can go beyond the first yield point. As part of that effort, we started expanding the Allen Davenport wind load chain. First, we introduced what we called first generation performance-based wind engineering framework. Basically, it is a deterministic process, but we were definitely setting different design target as it is done typically. The story global drift, peak floor acceleration, design bending moment, torsional velocity, even you have non-structural criteria, the pedestrian level wind and things like that. What makes this a little different from the typical wind load chain is the consideration of perhaps non-linearity and things like that. In its full-blown what we call next generation performance-based wind design, what we proposed and what we did was each of the design parameters, up to 14 variables, each of them can be represented probabilistically. For example, earlier when I showed the damping ratio, as opposed to using only 2.5, to use the information that, I'll go back quickly. As opposed to picking one value, why not we use this distribution information, the log normal distribution, with its 2.5 mean average? If you use this, and each of the wind will be represented by its distribution. The strength capacity of the material will be represented by a distribution. Then you conduct Monte Carlo simulation. Then the outcome will be represented in probability of failure as opposed to one magnitude exceeding this threshold or something like that, you know. And that kind of approach where you propagate the uncertainty throughout the design process and you present the final outcome as a probability of failure could be more representative of the design process and the performance of the building, you know. That is where things are going. Actually, there is a pre-standard in performance-based wind engineering that was released by ASE. It's a matter of time that majority of the design will start following performance-based wind design. You know, earthquake is a little bit advanced in performance design. The fire community is also following that type of procedure. And when, due to complexity, we were slow to kick off, but now many researchers are working, including the group at Western, on this topic, you know. Okay, for the 30-story building, actually, we did a probabilistic performance evaluation where we identify 14 parameters and represent them with some sort of appropriate distribution as suggested by other researchers from literature, you know. Then we follow two limit state based on habitability criteria, the 15 milli-G for residential building and the 25 milli-G criteria for office building according to NBCC, for example. Those are habitability criteria. Of course, there are criteria that the bound layer wind tunnel uses, RWDI uses, the International Standard Organization uses. So whatever is acceptable to your design office, you can use those habitability criteria. And there are deflection criteria like H/500 type of deflection criteria, you know. Then those are the limit states. Then we use this combined probability distribution and integrate them to get the probability of failure. Then, as opposed to having a single line that tells you you pass this threshold or not, then now you could provide full probability failure. You know, you could run Monte Carlo simulation with, for example, damping ratio 5% as a mean or 3% as a mean with a log normal distribution, and you keep running that Monte Carlo simulation, and for different damping ratio, then you give the probability of failure. You know, the first is habitability for habitability limit, the first two. The second is deflection. You know, then this type of information is useful for the designer and for the developer. Once they decide what level of failure they are willing to absorb, then for your design velocity, you can pick. You can know if you are satisfying the probability of failure or not, you know, for different damping ratios. So this is more comprehensive and gives more information than a typical deterministic type of analysis. Again, there's a beautiful review paper that Matthias Bezabe wrote. I encourage majority of, I mean, whoever is interested to read this paper. And actually for his work, Matthias received the Best Scientist Award during 2018 Wood Conference on Timber Engineering. And there is, if you are interested in the reliability analysis, you have this paper. Okay, moving to the second project, you know, a simple question was raised, you know, among us, and really, do we need that concrete core, or we could have gone away with only timber core, you know? Then we designed the structure again with a concrete core, since we didn't have access to the original design. by ourselves, and whatever we saw in literature in terms of the period, we were matching it, so we were happy. We were very close, at least, For example, FAST and UPS, the structural engineer of record, they reported this periods, and this is what we got, and it was close enough. Then we were happy. Just we stopped there. Then we replaced the concrete core with timber core, and we redesigned it. As you can see, the periods are higher, or the frequencies will be smaller. In wind engineering, we like to talk in terms of frequency, not period. Okay. We analyzed the Vancouver meteorological data. This is wind rows, and primarily the strong wind comes from the east direction. Typically, when we do serviceability analysis, we use low mean return periods, 10-year return periods and things like that. For load, it is 50 and above. Since it is serviceability, that occurs majority of the time. We focus on low return period wind events. Then these are the result. The one on the left is for full timber. The one on the right was RC core. Definitely when you have RC core, red. The red is the acceleration criteria. For residential, and the dark line circle, as it is defined here, it is a criteria for office. And the Brooks Common building being a dormitory, it is residential. Then if you consider again our target dumping, the blue with 2%. If it is concrete, definitely it's only 18-story in this short building, and we will not have issue. It's far from the criteria. But 18-story timber is approaching almost the criteria for residential. Barely satisfied it. Actually, this building was lucky because if you see the significant wind is coming from east, but because of the buildings, significant buildings in the east direction, it was sheltering it, and that kind of reduced the impact. Otherwise, if this building was there, mind you, for this weak wind, we were getting almost 50 millig, 50 millig for the timber core, But on this side, it is because of the sheltering, you don't see the peak, So that confirms what I was saying, surrounding conditions are important in addition to the signature or the aerodynamic shape of the building. But in any case, for this building, even if you use CLT core, it would have satisfied, the serviceability criteria. By the way, the ultimate state for strength is satisfied by all designs that we are discussing, okay? It is the governing is the serviceability here. Okay, on the 40-story, we did also similar exercise. And instead of the concrete, the timber core this time, because we saw it has issues, we replaced it with concrete core. And the moment you replace it with concrete core, I couldn't see the numbers, they were hidden here. As you can see, the fourth and the fifth mode with concrete core, they were above 1 Hertz now. For timber, they were below 1 Hertz. So we don't need to participate these modes in the wind analysis, Okay, then when you use RC core and with a damping ratio of 2%, you satisfy both the residential and the office criteria. Earlier, with a timber core, we have seen we were not satisfying those criteria. So hybridization is a good solution. Yes, as I already said, hybridization is a good solution, and there are also other solutions, one is aerodynamic. Maybe I will start, since I was already talking about the structural mitigation. Let me finish the hybridization concept first. I used to work in Miami, and I have seen firsthand how well this palm trees withstand hurricane force. When the hurricane hits them, they bend too much, and the mass flips it back to its original position. The wind bends it, and the mass brings it back because the mass wants to retain its original position. Then, if you have a heavy mass, lamp mass like this, it's a good acceleration solution. Yes, in terms of other issues, you have to watch out, but for accelerations, is a good solution. This is what the Norwegian engineers who designed this used also. Although this timber building is entirely made of timber, just to add additional weight, the last 6 floors were made of concrete, to have heavy mass at the top, similar to the palm tree concept. That was very neat, And so you can do this kind of structural hybridization mitigations, The other solution is aerodynamic mitigation. When I was working in the industry, there was this building that came to the lab, and originally the building has this kind of chamfering, shown, the depth shown by the 2 parallel lines. Then there was an acceleration issue, Then we recommended to make it a little wider, inspired by, like, for example, when you have chimneys, if you put a spire groove on the chimney with a dimension of 10% of the diameter of the chimney, it will kill the vortex shedding, So spires, chamfering at the corner and things like that, they have similar effect, So we were inspired by that, and we decided to test, and the architect agreed to us. And when we tested, we reduced by the order of 3 milli-G acceleration. Of course, that was not sufficient. We used structural fine-tuning, and we also added external damping. Then through the 3 solutions made this slender structure acceptable, So you have aerodynamic, that you can play with the exterior details of the shape, and structural, as I have been talking, like earlier. And if these 2 reduce it to a manageable level, or if they satisfy, okay. If not, you use additional external damper, But majority of the time, without even the use of additional damper, through aerodynamic optimization, as it is shown here, you can do a lot of amazing work, Especially now, the way we are using computational wind engineering to support the experiment, support wind engineering solution is amazing, Like earlier, as I said, here we didn't, in the wind tunnel, we cannot test, more than 5 or 6. It just quickly becomes expensive. So usually the solutions that we bring are the best of maybe 10 alternative solutions and things like that. But in CFD, you can deploy low order model and such wide combination of parameters, and most likely you can nail down the geometry detail that gives you minimum drag, minimum lift force, So that's where I see actually where computational approach in wind engineering could be very useful, And in this particular example, one of my former PhD student, Elshair, he's a professor at Lakehead now, did beautiful work here, Basically, what we wanted is to decide which type of detailing, shown by the alternative dotted lines, performs better for lift and drag, Sometimes the drag is dominant, sometimes the lift is dominant. So we need to have a mechanism to reduce both simultaneously or one of them individually, you know. Then what we did was we generated like some 200 combination of geometry and ran a CFD model. And we generated a database of the response for 200. And we thought even that was not sufficient, and we trained a massive artificial neural network model that learns from this 200 model. And we use this neural network model to generate the response surface almost continuously for all geometric parameter combination that is shown here. Then if you have the response surface like this, it's a matter of finding the value in this. And that point, you read the geometric combination, and that geometric combination, for example, for lift, is shown here. And this is the most effective corner mitigation with single recession with two straight line combination, you know. And the CFD can be useful, you know. That's what this could be very useful. Actually, it's not something new. As I said earlier, in the wind tunnel, people have used, for example, RWDI used chamfer, two-step chamfer for type A 101, where they managed to reduce the dynamic across load by 40%, you know, and the total overall load by 25%. And mind you, in tall buildings, design for lateral load is the most expensive part. And if you manage to reduce the load by this percentage, it has big economic safety margin implication. And the Swedish building here, beautiful twisted building, and the tapering also helps. And of course, the most obvious is leaving some open floors, you know. There is no cladding, means there is no wind load, you know. Okay, actually we used this recently as when we were advising the PMX 35 sidewalk lab, you know. We were exploring different kind of combination. For example, if one introduced balconies on the side to give this kind of corner details, then what was the red would reduce to the black. Or in terms of pressure distribution, these are the original sections on the left, and on the right, these are the mitigated. You know, you see it kills the load, you know, and the lift vibration as well, you know, responses. Actually, all this are coming as part of a chapter in the Advanced Analysis and Testing of Systems for Design handbook by FP Innovation. And as I said earlier, we tried it on PMX 35, but unfortunately, that, as you all know, that program got cancelled last year. Okay, I know I'm almost running out of time. My last 2 or 3 slides are pertaining to tornadic load. Usually at WindE, the way we generate tornado, we have this kind of system. If you see, you have a hexagonal dome inside and a hexagonal, which I show partially on the outside. You know, whenever you see orange color, it is a location of the wind fans. You know, then you can inject wind. Either you suck it through the exhaust fans or inject wind through the base fans in oblique direction, and that produces circulation. And through exhaust fan, if you suck it, you generate tornado, you know. And the tornado structure, you remember when I showed you the velocity profile earlier for straight wind, it starts from 0 on the ground and parabolically increases until it becomes constant. But for tornado, it is this kind of belly type of profile, you know. It is totally different type of profile compared to straight wind. And obviously the response that it produces will be totally different as well, you know. The load distribution, the load intensity dictates what kind of stress or response is going to be produced. And also it is characterized by deep suction, deep or high atmospheric, negative atmospheric pressures, you know. If you see the typical atmospheric pressure is here at the core of the tornado, it is very deep, So these are some of the characteristics. And if you see this tangential velocity, which is peaking at close to the ground, it varies from the core, showing as shown with the red line here. It increases up to what's called the core radius. That's where you get the maximum velocity. After that, it reduces. Okay, so we conducted two types of tests. One, what we call stationary tornado, where we located the building. This is stationary, the tornado is not moving, but we located the building where we thought is the radius, the core radius, or where the tangential velocity is the maximum. We did this kind of testing, one on the 10-story tall timber building. And the second, we located the building and we translated the tornado on the building, And of course, we tested for different orientation of the building as defined by theta here. Even for the stationary, we conducted multiple tests by rotating the building, The tornado translates like this. First time with theta 0. Next time, theta 30, theta 60, theta 90, That way, the tornado passes in different direction, orientation of the building, producing different kind of force, Then we designed the building with a Toronto design wind speed with a safety factor of 1.4. And we compared it with EF0, EF1, EF2, EF3, EF4, EF5 tornado with different level of damping, Usually, I don't like picking a specific damping. I like to give different results for different damping. Then it's up to the structural engineer. They know they have a better picture of the damping ratio, and they can pick and use the one that resembles their damping ratio. These are some of the pressure coefficients for stationary and translating tornado. The one in blue color on the left are all for stationary tornado. Stationary tornado, you can depict it with one velocity, with one CP, more or less. But as a tornado passes over your building, the CP changes, it's not like static. It's not stationary. It looks like this, as the showing on the right. Then we calculated the deflection using the time history load that we get from the load. These are the deflection, the top displacement. And if you see, this is the maximum interstory drift at the top. A is for 0-degree orientation, 30-degree orientation, 60-degree orientation, and 90-degree orientation. If you see, for example, for 90-degree orientation, the building that is detailed with LEPCC for Toronto wind speed is okay for EF0 and EF1, but EF2, 3, 4, 5, they exceed this, So when you have this type of tall timber buildings in the Midwest or in tornadic region, you have to check this, These are the shear forces. The one that is detailed with straight wind for tornado wind speed is good for E0 tornado, but as you can see, in terms of loads, all the E1 up to EF are greater than the typical design wind speed we have to do. So we have to factor this in our design. Okay, more publication are provided here about the tornado and the optimization. I'll take 1 minute to share my opinion about future research direction. Definitely understanding the inherent mass timber building damping is very important. We have to keep monitoring full-scale instrumentation and bringing innovative structural hybrid system. The beauty of mass timber is it is so constructible. It is lightweight. you can fabricate it somewhere and bring it. Then when you combine it with concrete, you lose that advantage. So carefully, you can hybridize it with innovatively with manufacturable construction materials. You could engage aerodynamic and dynamic optimization. Honestly, at this time and age, where you have significant computational resource and methods, efficient numerical algorithm design should be optimal as opposed to typical design, and also with the computational resource we have, we can scan it into a neighborhood design level, risk at a city level, and using some digital twin techniques, bringing our buildings and cities in the virtual world and doing our computational process and assisted with artificial intelligence. And with this, considering the positive sustainability implication and the resource we have, tall wood becomes a norm, especially now in the majority of Canada, up to 12-story is approved, is allowed. So even with a good engineering detail, we could go also beyond that. And thank you for your patience and understanding. I would like to acknowledge this funding agencies, NSERC Discovery, the Canada Research Program, and the research equipment from Canada Foundation, including the WIND-E and Ontario Center of Excellence. Honestly, to do research in Ontario is great. Ontario Center of Excellence is a big supporter of research, and FP Innovation, the timber experts, I'm very blessed to be associated with them and our labs, SOSIP, SharkNet for computational resource, SOM for allowing us using their concept design. Thank you.
Excellent. Thank you very much, Professor Girma. It was a very informative and interesting presentation.
Thank you.
So we've got some questions that came in during the presentation. Please take the time now, if you have questions, to enter them into the Q&A function. While we're waiting for questions, just two quick announcements. We actually have a workshop planned on earthquake modeling and responding to the new earthquake science that's going into the National Construction Codes in the next round. On January 26th, we'll have representatives from all the major modeling agencies, RMS, AIR, CoreLogic, as well as NRCan here talking about modeling on an online session. And I'll provide a contact for Tracy Waddington if you'd like to participate. Anybody on the line, please do contact Tracy and we'll send some information on that. So Professor Girma, there was actually a question concerning, and you went into detail about this, the hybrid design of buildings, including the different materials, concrete and wood.
Yes.
You offered a number of solutions where concrete may not be necessary. In the case of the Brock Common, they included the concrete in the structures you mentioned.
Yes.
So is this a common practice? Are designers looking for alternatives such as those that you recommended, aerodynamic design and other? And another question for me is, in BC, is there sort of like an interplay between the wind design requirements in the code and the earthquake hazard requirements, and that also affect the decision in Brock Common to include?
Yes. Both are excellent questions, Dan. The first one, when you are the first, like to do something out of the norm, like a few years back, constructing 18-story timber building was a brave undertaking, by the designers, Then, of course, they were very super careful. That's why they put the concrete core, Now that we know it is working well, but as a researcher, we can look into alternatives. Honestly, for that short building, maybe if they had used also the CLT, and it may expedite even the construction, and it could have been okay as well. But the concrete core was definitely significant safety margin, Yes, I think there is always different conflicting objectives that we have to consider, like one of the attractive nature of timber is its constructability, like if you see tall building construction in particular and building construction in general, a trade-based and very slow process, the industrialization has peaked, in the car industry, other venues. But when it comes to building, you don't see that kind of industrialization, maybe timber could bring that one, because you can fabricate it and it's easy to transport. One of the common challenge was if it is concrete, for example, it will be a daunting task, to bring all things on site, the space requirement, the transportation requirement. But with timber, it is compact, light, it is easily manufacturable, sustainable, and you can do that. Then, without negating that expediency, if you hybridize it, in the select places, like only link beams or perimeter beams or with steel and things like that. For example, my collaborator, Dr. Solomon from UBC, does a lot of outrigger hybridization. Researchers in FP Innovation, they are looking for different kind of hybridization. I think we shouldn't stick out our head and claim, I will only do concrete or only do timber. In engineering, use each material appropriately, utilizing their best advantage. Then it is a sort of optimization, not only from strengths, constructability, serviceability, through some sort of life cycle cost analysis. If you do that, then you end up producing houses that are quick to construct, sustainable with less environmental impact, and safe also to dwell in them. The second question, the aerodynamic optimization, the structural optimization, they were there in the industry. People have used it. For example, the Torosso Tower in Sweden, that twisted building, it's elegant. We tested it in the Bond-Blair Wind Tunnel. In fact, before it predates me, before I joined Western. And I worked on Dubai, Burj Khalifa, with Peter Irwin, one of the best wind engineer in David. He was my boss, like the structural engineers and architects, they were inspired by a desert flower, and that shape that you see in Burj Khalifa, it is organic, it is natural. Usually natural shapes, they are more aerodynamic, nature is smart, Then the tapering, the shape and everything lends itself to reduce loads, But what is new now is the utilization of computational tools to find which combination of shapes, which alternative is even more better, It is a degree of accuracy, or what we are getting to near optimal solution. Before it was a better solution, now we are approaching near optimal when we utilize the computational resources around us. Then what we are doing now, since timber is constructible, we can bring these techniques even in more magnitude, because timber lends itself, like if you want to tweak the shape, if you want to construct very complex shapes and things like that, that's my excitement, when it comes to timber. So basically with timber, what we are doing is understanding the strengths and weaknesses of timber and bringing the latest technology like performance-based design, aerodynamic, structural dynamic optimization, and we try to do our best in the new opportunity that's coming to the industry.
Oh, great. Thank you for the response. It's good to hear your enthusiasm for the potential of this approach. One last quick question. We're getting close to 2:30. There are a number of questions, but we'll try to squeeze at least one more in. Just for the sake, I suppose, of clarification, and you went into quite a bit of detail about the peak acceleration issue and how that's a consideration for this type of construction. Is this strictly a comfort issue? Are there safety, collapse issues associated with this? What's the...
Yeah, so serviceability, there are two types of serviceability criteria. So when it comes to the one you asked, acceleration, it is a comfort issue. It's not a strength issue, it is comfort issue. People could feel dizzy, people don't feel comfortable, people could throw up, and it is also very subjective, like some are very tolerant to motion, some are not, so it is divided through interview and in-person, like putting people in moving rooms and interviewing them and things like that, So these are more serviceability, the acceleration criteria. The deflection, of course, it will crack, like for example, one of the tall building in Chicago where it was built, because of excessive deflections, the cladding was cracking and falling down from up in the sky, to the pedestrian level and things like that. The last thing you want to see is, yes, the structure could be strong, but even that significant motion could lead into breakage, or if the buildings are close to each other, bumping to each other and things like that, So still serviceability with implication to safety, but the acceleration is primarily safety. I remember a question you asked that I did not answer as well, like earthquake happening with wind, Yes, in some places, like for example, the Taipei 101 building is a good example in typhoon area and earthquake area, and when you have that, you have conflicting objectives, For example, for wind, we need to have big mass on the top. I don't think the earthquake likes that one. And for wind, we like discontinuities, irregularities in the shape to break the vortex shading. I don't think that discontinuity is welcome in earthquake. Then designers are challenged to optimize for the two under constraint, conflicting objectives. Yes, we deal with that in design, but luckily many cities that are dictated by one or the other. But with tall building, by the way, wherever you are, whether it is earthquake prone or not, the moment you pass certain height, wind becomes, wind gradually increases as you go higher in height, So the wind will take over, as the building become taller and taller, irrespective of the area. But in some regions, yes, the earthquake will still linger there, and both of them are critical design considerations, and hence we have to deal with the constraint, conflicting objective optimization. Yes.
Okay, excellent, very understood. So we're very quickly nearing 2:30 p.m. Eastern time here, so we may have to leave it here. There are a number of additional questions and also several attendees commenting and thanking you for the very interesting presentation. Many people asked thanking you for the presentation.
Okay,
so
thank you
again.
Thank you. If you pass the questions, what I could do is maybe I can respond in text and upload it when ICLR post the video. We can post the answers as well, or I can post them in my LinkedIn as well.
Sure, we'll make sure we get those questions to you,
Okay, thank
and
you.
we'll put them in the YouTube video. And I should mention quickly, there was some questions about whether we post this video. Hopefully, you'll be okay with us posting this on
Yes.
our ICLR YouTube site, so that will be available. And so, thank you again,
My pleasure.
Dr. Girma, and
pleasure.
I'm sure we'll be hearing from you again in the future.
Yeah, thank you. Thank you very much for inviting me and for everything. Thank you.
Great, thank you. And thank you everyone for attending. And with that, we'll close the webinar.